have touched upon predictive models and how to apply them in practice and pharmacogenomics, and now we will go to traditional area of diagnostics, computer visioning in medicine. And now the floor goes to Olga Puchkova, head of Mammology Center of Ilyinsky Hospital, and Alexandra Yalunin, chief data researcher from AI Sber lab. Please, you're welcome. Now we will show you our article. This article was prepared this year and offered for the conference. So we will show you how we work, how I work with data. 4 images of mammograms, and at the end we want to have a result, conclusion showing all the data on the images. Alexandra, no slides yet on the screen. Could you please share your screen? Colleagues, I'm sorry. Yes, please. So these mammograms show the status and the model we are offering, and then the floor goes to Olga. Good afternoon. My name is Olga Puchkova. I am X-ray doctor. For more than 10 years, I've been diagnosing diseases in breast screening. I'm going to speak about this. You know, many doctors lacking data on artificial intelligence are resisting such technologies, but we understand that without artificial intelligence, there is no future, and all breakthroughs in medicine will be assisted by AI. Why it is important for breast diseases? We can have a look at data saying that more than 2 million cancer cases are registered across the world annually, but 627,000 women die due to cancer, breast cancer, despite all technologies we're having today to cure such disease. Next slide, please. And now I would like to speak about how the diagnostics and treatment for breast cancer developed. So it existed for more than 5,000 years, but over this period of time, we were able just to monitor and to observe how cases develop, and there were no treatment. And then in 1981, Halsted treatment was invented. This is invalidizing operation treatment that was offered to women at that point of time. But unfortunately, quality of life of such patients were around zero after such treatment. And mammography came in the 70s. It was a revolution in diagnostics of breast cancer that allowed doctors to find the cases even before you can feel it with your fingers, and reduced by 60% the mortality rate from breast cancer in the countries where there are programs for early diagnostics and screening. I will tell you more about it a bit later. Of course, we are going towards personalization. I would like to say that personalization in diagnostics and treatments is only possible basing on data we mentioned, genome data and data on additional medical data like proteome, transcriptome, and some other omes we are talking about today. And the combination, the mixture of them, will allow us in the future to be efficient in our diagnostics and offer efficient treatment for our patients. But this is the future, and today we are in the area of mammography now. Next slide, please. I would like to say and clarify what screening is all about. Screening is screening for absolutely healthy people. Patients do not go to clinics, so they just can be at home and have a call from us, and we just tell them we want you to be healthy. Please visit your doctor and have an annual checkup. We just want you to be safe. And the main aim of every screening is to reduce mortality rate from such disease, and that's what happened to mammography. In Sweden, as of now, the morbidity rate dropped by 60%, but the problem is that so far we are yet at this 60% drop and we're not moving forward due to various problems we're facing. I'm going to speak about now, and in the future I think we will resolve these problems through machine learning. What early diagnostics allows us to do today, and why mortality rate dropped so dramatically? This happens because, and we know through genetic research, we know that up to 14 millimeters inflammation, we can make proper diagnostics and reduce the mortality rate. So when oncologists, cancer experts meet each other on international platforms, we see that early diagnostics allows us to be very effective in our treatment and save the breast and it improves the quality of life of women, and it means a lower level of surgeries and making lives of women better. Next slide and next one. Here we have a couple of problems we are still facing. This is the speed of reading mammography. So far today in Russia it is 20 mammography images in 6 hours. In the Netherlands, it is 350 cases in 3.5 hours, but this is not enough to cover the all mammograms that are accumulated through screening programs accumulated by doctors for further interpretation. Next slide. The problem we are facing today is quality of conclusions. We carried out a test in a region of Russia where we plan to launch screening program, showed that using real tests, when we show the views, asking radiologists to interpret them, it turns out that out of 46 doctors who were allowed, actually only 4 were competent enough to work in this area. So the level of competence turned out to be quite low comparing against requirements we have for the screening program. We know that per 1,000 screening cases, we can find around 5 to 7 cases of breast cancer, and it means that 993 cases will be absolutely normal, and the majority of doctors today spend much of their time to read and interpret normal cases, and it takes around 5 to 7 minutes per each case, depending on the complexity of the images we are having. So it turns out that the main load is actually covering cases of absolutely healthy women, and the cases that actually call for real doctor's attention are actually in this area of the main cases interpretation. Next slide, please. And today, artificial intelligence and the solution that were developed in the lab of artificial intelligence of Sberbank allows us to automate routine processes, and doctors have opportunity not to interpret those changes they see in the images, only receiving important cases and images where it is really important to put more attention into with by doctors of high qualification and competences. And another problem is that when we actually look at the cases, we have false positive and false negative cases.
And other women patients should not be called up. So we are aware that many models were developed AI. Using AI allow us to reduce the frequency of false positive, false negatives, and also as support for the radiologist allow to prioritize the interpretation of images most abnormal can be filtered and screened. Automatic protocols based on image recognition protocols are used. We heard of omics technologies in radiology. It is radiomics is developing, which will allow in the future not only to reduce the workload of the doctor, of the radiologist, also reduce the number of false positives and negatives. But also it's important that today we have programs and models in place based on just image recognition to predict with accuracy the type of breast cancer, which the optimal treatment protocols fitting the patient. Certainly research is ongoing. It will be combined with genetic and other research, but certainly without machine learning, this future of the industry is impossible. Thank you. Thank you very much. Now let me tell you about the architecture of the model providing this result. In this article, we use the first framework, using deep learning, creating the mammographic report and visualizes the model. Using BERT, it uses encoder-decoder architecture. I hope you can see it, dear colleagues. So the encoder here receives a set of projections and uses a neural network to filter this. Then decoder, based on transformer, creates a full report based on image recognition and processing. The data set is based on screening programs in one of Russian regions. Over 25,000 mammographic radiology tests were used in for projections and clinical report. Some 7 binary bits of data representing the changes in the tissues, lesions, shadows, classification of rows, listening by-rates 2. These targets are used for encoding. The total architecture is presented here. The encoder is efficient net that we're using 4 times. We also teach it to predict targets. We extract the feature maps from the last search layer, and that's how we receive the 4D image, which we use for linear transformation. BERT is used for decoding, and the previous layer is sent as a request. The matrix is also processed by the encoder. This allows generated sequence to focus on all areas of images, which allows for text-to-picture mapping. Model variants are randomly initialized BERT with no attention. The second uses the previous attention mechanism. Then we use the, once again, randomly initiated BERT, trained on corpus of Russian text and on medical data, over 150,000 of case histories. And quality and precision is measured Blue Rouge, Meteor, Cedar. And we also conducted an experiment with certified radiologists, presenting a new panel of 150 data sets, where we compared random to factual reports. We asked each doctor to assess each of the reports, random, factual, and for clinical models. Here you see the automated evaluation and the doctor evaluation. The doctors provided a score on a scale of 1 to 10, and we saw the following observations. First of all, using attention mechanisms improved outcomes. Also, BERT showed improvement compared to others. BERT pre-trained on medical corpus also improved accuracy. To interpret a generated report, we visualize the memory cards between text to data to picture. We are also analyzing correlations between the areas that the model is highlighting. In our article, we analyzed 6 cases. Here, 2 of these are quoted. First of all, The model looks at the glandular tissue, doesn't classify it as an anomaly, so it can well predict the breast density, which is very interesting because, first of all, this can prevent for cancer screening. The structure of the mammary glands type 1 is also detected by type. Also, the model detects the quadrant, the areas of the breast where the anomalies show. This is how the models detect and describe malignant tumors, which can lead to high PV during pre-screening. So this is the outcome. The article presented first framework using mammograms with deep machine learning for interpreting the process. Attention model is also used. This method discovers new opportunities in screening, visualizing attention maps between text to image, providing for semantic and visual interpretation of breast cancer screening. The doctors also vouch for the technology. Our best model successfully describes pathologies and describes the anomalies. It is in open access and can be located using the link on the slide. Thank you. Thank you very much, dear colleagues. Unfortunately, the time passes quickly, and we practically left no time for answers. However, those in the audience, if you're interested, please ask your questions through the online form. They can be passed on to our colleagues to be replied. You can also write us direct and leave your email. They will provide their details.